Alright, so this is the second video for molar mass and dimensional analysis. Where we left off last video is for this last conversion factor here, and that is talking about moles to liters, how I convert between that, but it has a very specific time when I can use this conversion factor. It can only be used at STP. Now what STP stands for is standard temperature and pressure. So the temperature has to be at 0 degrees Celsius. In Kelvin, that would be 273 Kelvin. And the pressure has to be in 1 atmosphere. If we do not have these conditions, we cannot use that conversion factor. What we will have to use instead in order to convert between moles and liters is your PV equals nRT equation, where this is my volume and that's my number of moles. So again, only use this conversion factor at STP. It will tell you STP or give you those conditions, 0 degrees Celsius and 1 atmosphere. If not, I have to use PV equals nRT. The next thing that you'll have to be able to do, and you use this very widely throughout this course, is the molarity equation. So first of all, let's explain what molarity is. Molarity is synonymous with concentration. So think about it. If I have lots of Kool-Aid powder in a solution, then that is highly concentrated. But if I just put a little bit of Kool-Aid powder in a solution, then it will not be as concentrated. It will have low concentration. The same thing goes on with these chemicals that we're making in solutions. So if I take a solid and I put a lot of that in water, it will be a highly concentrated solution, and concentration and molarity are synonymous. If I just take a little bit of solid and put it in the same amount of water, then that is going to be a less concentrated solution, or it will have a lower molarity. So when we're working with molarity, the equation that we're working with there is moles of your solute, that's the stuff you're dissolving, over liters of that entire solution. Make sure that you are using liters here. You cannot use milliliters or anything else. It has to be in liters. The next thing I want to go over before we get into some example problems is looking at multiple relationships. This to me is a very important factor because that's what stoichiometry is all about. It's about multiple relationships between elements within a compound, between polyatomic ions within a compound, between ions in a compound, or even between things that are in an equation, so compounds that are in an equation. So this is really important. This is going to help you out a lot. So if I wanted to say, what is the multiple relationship between Ca and Cl2, what I'm going to look at there is the subscripts, all right? Because there's nothing beside the Ca, it's understood one subscript. So my relationship between Ca to Cl2 would be 1 to 2. I can also look at it from a whole standpoint here. I could say, what is the relationship between iron 3 nitrate and nitrate? So what's the relationship between iron 3 nitrate, which is the whole entire compound, and just your nitrate ions? Well, my relationship there would be 1 of the iron 3 nitrate, 1 entire compound, is equivalent to 3 nitrate ions. So it's very important to be able to look at multiple relationships within these compounds here. Now, I can also take it to a larger scale. When I'm looking at balanced equations, I can understand the multiple relationship between hydrogen and oxygen, or oxygen and water, or even water and hydrogen here. So where I'm looking at for my multiple relationships within an equation are these coefficients right here. So I have a 2 to 1 relationship between hydrogen and oxygen. So that's a 2 to 1 relationship. Between oxygen and water, there is a 1 to 2 relationship. And then if I want to compare water to hydrogen, it's a 2 to 2 or a 1 to 1 relationship between them. Now, where this is going to come in play is a couple of example problems when we're doing our dimensional analysis. We have to be able to set up our dimensional analysis using these mole-to-mole relationships to get from one thing to another. So if I want to get from moles of the whole compound, iron 3 nitrate, to just moles of this nitrate ion, I have to use this relationship somewhere in my dimensional analysis. Okay, so for example 1, we want to be able to calculate the number of moles and mass of a sample of cobalt that contains 5 times 10 to the 20 atoms. So if you look here, we always start with what's given, all right? So we're always going to start with what's given. And what we want to get into is two separate things. We want to get into moles, and we also want to get into mass. So we're going to have to do two separate dimensional analysis here. So I have them worked out, so I can go through this with you. So let me see if you can get a pretty clear image here. So we always start with what's given here. So this is the 5 times 10 to the 20 atoms. Now we have to look at the conversion factors and figure out which one we're going to use. So we're going to use 1 mole is equivalent to 6.02 times 10 to the 23rd atoms. Now the reason why we're going to put atoms on the bottom is so it can cross out with the atoms that we have here on top. Now we're left with just moles of CO. So that answer that we get is going to be the moles of the cobalt that we have. So remember that you multiply across and you divide if it's on the bottom. So if I take the 5 times 10 to the 20th divided by 6.02 times 10 to the 23rd, I will get 8.31 times 10 to the negative 4th moles of cobalt there. For my second portion, I want to figure out the mass. So what I'm going to do is take those moles, the 8.3 times 10 to the negative 4th, and I'm going to use the conversion factor of molar mass equivalent to a mole. Now again, I want to make sure that I cross out my units. So since moles is here, I want moles to be on the bottom so that unit goes away. So I'm left with grams on top. Where I found this gram amount is I looked up cobalt on the periodic table. So that's the whole molar mass we were talking about at the beginning. When I do my math there, I get 4.89 times 10 to the negative 2 grams of cobalt. It is okay to leave this one as 0.049 or 489. That's totally fine. Usually I like for you to put it in scientific notation if it's to the negative 3 and greater, or actually a smaller number, or to the positive 3. So, and remember that we need to have 3 significant figures when we're working with our numbers. So now I want you guys to do example 2 and have it for class tomorrow. Now for this next one, this is where the mole-to-mole relationship is going to come into play. So we want to figure out the mass of just carbonate ions in a sample of calcium carbonate. So we're going to start with the information of the calcium carbonate it gave us, so 4.86 moles of calcium carbonate. And since we have moles of this whole compound, we need to figure out how many moles of just the carbonate ion is present there. So this is where our mole-to-mole relationship is going to come into play. In one compound, there's one carbonate ion. So that's why there's a 1-to-1 relationship. Now, calcium carbonate needs to be on the bottom so these units here can cross out. The carbonate ion is on top. Once we're in moles of the carbonate ion, I then can get into grams because of the gram to mole relationship that you have there. So I have 1 mole of carbonate ion is equivalent to 1 mole of carbonate ion, which is equivalent to 60 grams of the carbonate ion. Now that I see that all my units are crossed out except for what I want, grams of carbonate ion, I now can do my math. So I'm going to take 4.86 times 60, and that's equivalent to 292 grams of the carbonate ion. Now, I want you to also do example 4, and then I want you to give a stab at example 5 and example 6. Those are dealing with molarity. So work on those, and we will go together, work them out together in class if you have any trouble.